Okay, chapter 25, doing the problems here. Problem 1, be able to solve mathematically and using ray tracing to find the image locations and sizes for the following scenarios. And I have 3 scenarios. Now I'm going to do the ray tracing first just because you can always check to make sure you have the answer right, but I always like to do the ray tracing first to make sure I drew it right before I do my check. So the first job is to carefully lay out your scenario. So here we have an object that's 1 centimeter tall that is 15 centimeters away from our, in this case, I have a mirror, there's a lens. I'll do the lens first, and then I have focal lengths of 8 centimeters. Now, one thing you'll notice right away is I don't have the same vertical scale as I have horizontal scale. That's okay. You can have different scales in these ray tracing diagrams. Now, I need to draw my 3 rays that we talked about. So we have the parallel ray that goes from the tip of the object parallel to the principal axis and then refracts through the primary focal point. So let me draw that one. I'm using OneNote here because I have a ruler tool. So there it's going parallel to the principal axis. The principal axis is that black line that's going through the center of the lens. And then it comes out and goes through the focal point. Now keep in mind, you're never going to be absolutely perfect on this. Even though I'm using a ruler, I'm still not going to be absolutely perfect because you have to get things exactly the right place if you're going to be absolutely perfect. Okay, the second ray will be the focal ray. And it goes from the tip of the object through F prime in this case. Well, it's the focal point on the same side if it's a positive focal length. And then it refracts parallel to principal axis. This is exactly the reverse of the ray we just did. That is, the ray we just did went in parallel and came out through focal point. This is going to go out through the focal point, and then it's going to refract parallel. Now, the astute student says, okay, where those two cross, that's where they cross. But we always do a third ray to check our answer. So the third ray is going to be the vertex ray, and it's the easiest one to draw. It goes from the tip of the object straight through the vertex. The vertex is the location where the principal axis and the center of our optic meet. So it's going to be going, well, that wasn't quite right. That's not quite right either. Too much. Okay. That looks about right. Okay, so there's my O. It passed a little high here. I know it actually went through the place I want it to go, but I'm more concerned about trying to get the ray accurate than I am about having the right answer, believe it or not. So let's try that and see if that's better. It's still a little high, but that's what we're going to get. So now the image is going to be formed where these all meet. And once again, you are astute enough to probably recognize I have 3 crossing points. And I just always take the center of them when I'm not perfect. And so here is my image. This was my object. Now we were supposed to find the image position and the image height. So using my ruler, you'll note here, hopefully that the ruler scales. Yeah, good. I measured my height of my object to be 5 of these little marks, and the height of my image is 1, 2, 3. It's right about 5 as well. So I'm going to say that that's 5 marks. 5. Oh boy, that was bad. Wow. There we go. So I'm going to say this is the same 1 centimeter. Now I know it's not 1 centimeter. It's got to be a little bit different, but that's what I measured, so that's what I'm going with. Now for the image distance, I used each one of these ticks was a centimeter. So 1, 2, 3, 4, 5, 6, 7. You see 8 there's where the focal point is. And you can see my black line went too far. That's why they don't all match up together. 9, 10, 13, 14, 16, 17, 18. So I have distance image equals 18 centimeters according to my drawing, and the height of the image is equal to minus 1 centimeter according to my drawing. Now let's compare that to what it should have been. So now we're going to use the thin lens equation. 1 over f equals 1 over distance image plus 1 over distance object. We know distance object and f, so I'm going to solve this for 1 over distance image. Now I'll put in my numbers. And so I just take 1 over 8 minus 1 over 15, and that gives me, after some careful work, 1 over 17.1 centimeters. So distance image should have been 17.1 centimeters. Now, you can see I wasn't perfectly correct here because I had 18, but especially seeing that my black line there, the parallel ray, didn't go through the right spot, yeah, I'm pretty satisfied with that outcome. Now, the second thing is finding the height of the image. Height of the image. How do I find that? Well, magnification is defined as height of the image over height object, but through our geometry, we learned that was equal to minus distance image over distance object. So now that I know distance image, I just say height image is equal to minus height object distance image over distance object. Put in my numbers. Height of the object was 1.00 centimeters. Distance image 17.1 centimeters. Distance object 15.0 centimeters. And I have the height of the image equals minus 1.14 centimeters. So that one's a little bigger off, right? That's 14% off, whereas the first one was a smaller percentage error. So that's one of the 3 options I gave you. Now we have actually one of the 6 options I gave you, excuse me, because I have lens or mirror. So that was with a lens, here's with a mirror. How is the mirror different? Well, we have the same rays, and so I'll start with my parallel ray again. So my parallel ray is going to go parallel to the principal axis from the tip of the object, but now it's reflecting back through the focal point. So it's reflecting back like that. So that's my parallel ray. And then I have, using the same colors, my focal ray I did in green. So, yes, honey? I'm recording, baby. It's okay. So it's going to go through the focal point and come out parallel. That's about as good as I can get my ruler lined up, I think. And finally, my vertex ray. Whoops, I had the colors wrong. That should have been the red one. So I'll use a different color so I don't get it more confused. My vertex ray is going to go from the tip of the object to the vertex. Oh, that was not good. And then it needs to go the same amount below. So what I'm going to do is I'm going to actually measure the same height as I made my object down below. So I had that as 5 units. So right here. So it should go right through that little blue dot that I just made. Well, that missed. Undo. There's the cheesy way. Adjust everything down. That should hit now, right? Okay. And with that adjustment, they all meet at exactly the same place. So let's mark our image. I have no idea why that popped up. I am not fine enough with my motor skills. Dentist I shall never be, nor the artist. I was going to say, if I don't get it this time, I'm going to go with 89 degrees because I can get 89 degrees like a champion. So there's my image. Now the image height is easy to read because I already have this set correctly. And so that's 1, 2, 3, 4, 5. And let's say each one of these, so that would have been 5.1 there, or excuse me, that would have been 6. So let's say 5.2 or 5. Yes. 5.2 divided by 5 is going to be 1.04. Right, my scale was, each one of these marks was 1/5 of a centimeter. So that's why I have the divided by 5. So that's the height of my image. And keep in mind that's a negative height because it's upside down. Now for the image distance, the image distance is going to be 10, 15, 16. What do you say? 16.8. Now notice, this is 16.8 centimeters. It's a positive because it's on the side that the reflection should occur. So on the same side as the object is positive if it's a mirror. Up here for the lens, it was a positive image distance if it was on the opposite side because light should go through the lens. So you've got to keep those, what's a positive and what's a negative, correct. Now, there's my two answers. The value should have been the same as I had before. And so the correct answers were, again, 17.1 for the distance image and minus 1.14 for the height. So that's our first set. That was a converging optic with the object farther than one focal length away. Now this next set, B, is everything the same except for the object is closer than one focal length. So, by the way, notice for my lens, I have very carefully marked the center, not so carefully marked the curvature of the lens. So I have to do exactly the same rays again. So here's my parallel ray. And the parallel ray should go through the focal point. That dot is big enough for the focal point that who knows if it's the right spot. Now, I happen to know through my vast experience that, thank you very much, Microsoft, that if the object is closer than a focal length for a converging lens, it's going to give me a virtual image. So I'm putting the extrapolation here already because I know that just from what's given to us. Okay, second ray, I believe it was now red, is going to be the focal ray. So the focal ray is supposed to go through the focal point on the same side. Well, the focal point on the same side is behind, so I actually have to draw my ray going from the focal point through the tip of my object. And you'll notice here I have a bit of a problem. It's a little high for how high I drew my lens. So I'm going to take this and just extend my lens. Whoops. Extend my lens just the slightest amount. And now put my ray. So it's going to come out parallel. The focal ray comes out parallel. And once again, I'm going to extrapolate backward because I know, oh man, I know that's where it's going to be formed. It's going to be a virtual image. And now finally I have my vertex ray. So the vertex ray, boy, I don't even remember what color I did the vertex in. I'm just going to do it in blue this time. The vertex ray is the one that goes from the tip of the object through the vertex and keeps going straight. That looks about right. So the vertex ray goes like that, and I'm extrapolating back. So notice I use dashed lines for my extrapolations. Now I have all of these, and once again you can see, wow, my ray tracing wasn't perfect. And wow, I'm not super concerned because, you know, we're not going to be perfect when we do these. So my image, I have, once again, my crossings there, there, and there. I take the center one, I'm going to say that's what I'm using for my image position. So my image position, I'm going to put right there. If we measure the height of that image, we find that it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, just a little over 12. So let's say 12.1. Once again, divided by 5 because I use that same scale. So 12.1 divided by 5 is going to be 2.442, but we only have 2 decimal places. Centimeters is the height of my image. And the image position now the image is on the same side as the object, but this is a lens where it's supposed to be on the opposite side, so it's going to be a negative image distance. Go back 5, 10, 11, 12. Let's go with 12.1. So distance image equals minus 12.1 centimeters. So there's my distance image. Here's my height of the image. Notice the height of the image is positive in this case. Now comparing that to theory, I'm just going straight to the same 1 over distance image equals 1 over f minus 1 over distance object equals 1 over 8.00 centimeters minus 1 over 5.00 centimeters. And when you put that in the calculator, you get 1 over distance image equals 1 over minus 13.3 centimeters. So distance image should be equal to minus 13.3 centimeters. And then the height of the image is minus height of the object. Distance image over distance object equals minus 1.00 centimeters times minus 13.3 centimeters divided by 5.00 centimeters. And so that's going to give us minus and minus makes a plus 2.7 times. I said 2.7 times. What I have written out for my work is 0.889 times. 2.7 looks better than what I did for my work. I must have made a mistake when I did the equation on the spreadsheet. So here's my actual values for my picture of minus 12.1 and 2.4. My calculated values, minus 13.3 and 2.7. So once again, close, not exactly right. Now, repeating for the lens. At this point, it's starting to get hopefully repetitive. So you're not like, what? I'm not sure what to do. Start with that parallel ray. Parallel ray. And it's going to reflect back through the focal point. That looks like it's about good. And then I'm going to draw the extrapolation because, again, with the object closer than the focal point on a converging optic, I know I'm going to get a virtual. Okay, next ray we do is the focal ray. Once again, focal ray. It's going to be crazy. Goes from the focal point to my tip because I'm inside the focal point. Then it's going to come out parallel. And I'm going to draw my extrapolation. Whoops. I did my extrapolation on the wrong side. That's impressive. This is the side where the light's reflected. This is the side where it's extrapolated. And finally, the vertex ray. So the vertex ray is going to go from the tip of the object through, oh, come on. Tip the object through the vertex. And then it reflects exactly symmetrically. So I'm just going to, once again, mark where it should go through on the reflection. 1, 2, 3, 4, 5. It should go through that point. So it's going to reflect like this. Extrapolation goes back like that. And so you can see that the reflected rays never meet. So it doesn't form a real image. It forms a virtual image. The virtual image this time around, I'm pretty accurate. I don't know why it keeps thinking I want a keyboard. I also don't know why I am so uncoordinated with this tool. So here's my image. My image height is 5, 10, 11, 12, about 12.8, would you say? 12.8, 12.9? So height of image equals, I'm going to say 12.8 divided by 5, which would be, what, 26? That'd be 24, 25.6. So yeah, 26, 2.6, forgot the decimal, centimeters for the height of the image. And the distance image is 5, 10, 11. Let's go with minus 12.0. So there's my measured values. Once again, whether it's the lens or the mirror, I'm going to have the same theoretical value. So there should have been 2.7 and 13.3. So there we have our third and fourth, if you will, our second set. This was with the object closer than focal length for a converging optic. Now our final one is the object back at farther than the focal length, but now with a diverging optic. So for the final one, once again, 2 pictures. Surprise, surprise, surprise. We will start with the focal or the parallel ray. Boy, it would have been a surprise if I start with the focal ray. So I start with the parallel ray. The parallel ray is going to refract through. Now, I might have labeled my focal points incorrectly. I wasn't paying much attention when I did those. But it's going to refract as if it came from the focal point on the same side if it's diverging. Remember, diverging lens, it diverges, it goes away. So it refracts out like that. Because it's a diverging lens, it always forms a virtual image, which means that it's the extrapolated rays that are going to meet. So I draw the extrapolated ray. Next, we do the focal ray. Now, this is probably the trickiest of all of the rays we have to do. The focal ray for diverging goes to the focal point on the opposite side. So it goes from the tip of the object to the focal point on the opposite side. Now, it doesn't continue on that line, neither does this extrapolation. So I'm not continuing the line. But, well, I will right now put dots. Oh, seriously. Thank you, Microsoft. I love you too. Apparently, I won't put dots all the way. But that's the direction I aimed it. Now, the focal ray comes out parallel. So now I set this to 0. And it's going to come out parallel. Put my extrapolation back here because I know it's going to be virtual. And I have one left, the vertex ray. The vertex ray goes from the tip of my object through the vertex. Straight line. Nothing tricky about the vertex ray. That's our easiest ray. So you can see, once again, the transmitted rays don't meet. But the extrapolated rays, and you have to be careful here. So many times people have chosen the wrong place. They'll have the rays right, and they'll choose the wrong place. The extrapolated rays are the ones that I have in dashed, and they meet right there. And this was a nice image, so it's going to hopefully be also correct-ish. So let's measure the height right now. That height is 2. Height of the image is equal to 2 divided by 5 is equal to 0.40 centimeters. So that's our height of the image that I got from my, not experimentally, but from my ray tracing. And then the image position is going to be 1, 2, 3, 4, 5, maybe say 5.2. So distance image minus 5.2 centimeters, because for a lens, the image should have been on the opposite side as the object, but it's on the same side, so that's a negative image distance. So there we have our ray tracing result. Let's calculate what that should have been. 1 over distance image equals 1 over focal length minus 1 over distance object equals 1 over minus 8.00 centimeters minus 1 over 15.0 centimeters equals 1 over, and according to my previous calculation, minus 5.2 centimeters, therefore distance image should have been minus 5.2 centimeters. I got exactly that. Hey, that was pretty good. And then height of the image equals minus height of the object times distance image over distance object equals minus 1.00 centimeters times minus 5.2 centimeters divided by 15.0 centimeters equals, no, it's minus and minus again, so it's a positive, and that should be 0.35 centimeters. and I got 0.4. So that's as close as I was going to get. So that's my best drawing of the day. Well, there's one more to go. The mirror. Notice the mirrors, I just put little tips at the end to say which type it is. No surprises now. If you don't know which ray I'm drawing, you haven't watched from the beginning. I'm going to start with the parallel ray. Parallel ray is going to reflect back as if it came from the focal point on the other side. So it's going to reflect back as if it came from there. So it goes like that. And once again, diverging always makes virtual, so I'm going to extrapolate right now. There's my extrapolation. So there's my parallel ray. Let's go to the focal ray. The focal ray is going to go toward the focal point on the other side now because it's diverging. It's going to the opposite side. So it would have continued on. Hey, look, this time it worked. But it comes out parallel. So it's going to be reflecting back like this. And once again, draw my extrapolation because I know it's going to be virtual. And finally, my vertex. For the vertex, once again, I should have just done this the first time. It's going to hit the vertex and reflect back absolutely symmetrically. So that means 1, 2, 3, 4, 5. It's going to reflect back to there. Let's change the color. Let's go with red. So the red comes in. You can sometimes get confused on what your vertex is by this point. You got to be aware of what your principal axis is. Somehow my colors got messed up, but you should have noticed that I used black for my principal axis originally. It's just in the copy paste. Somehow I got the color changed. So here's my reflection. Once again, extrapolating back. And where's the image formed? It's where all of the rays, the extrapolations met. Now notice my little dots. That wasn't an extrapolation. That was just for aiming purposes. So my image, where those extrapolations meet, is right there. There's my image. The height of said image is right at 2. So height image equals 2.0 divided by 5 equals 0.40 centimeters. Same thing as I had in the last one. And the distance image, by the way, I should put a tip on there, is 1, 2, 3, 4, 5.2. Distance image equals minus 5.2 centimeters because the reflected light was going left. This is not the reflected, it's the extrapolated, so that's why it's minus. So 0.40 and minus 5.2, exactly the same as I got in the last one. Now you might wonder, why did I do better on these two? Because I was diminishing the size, right? The magnification for these is less than 1. When it's less than 1, it's actually going to help you to have less error. Okay, so that's how we do all of our ray tracings and, here we go. All of our ray tracings and use the equations. So the distances for the images for the 3 cases, right? I only have 3 answers here because there were only 3 unique answers. Should have been 17.1. The second one was minus 13.3. And the third one was minus 5.22. Actually, I should have that one more decimal place. My mistake. Use the magnification equation to find the magnifications. We found the magnifications to be minus 1.14 is what I should have put there. And this is the one that I had previously calculated incorrectly. So let's just look at what should have been. We had that would be 26.6 repeating, so 2.67. minus 2.67. Oops, that was plus 2.67. And the final one was 0.348. So these numbers actually got them from the equation, but you saw how I did them both different both of the ways. Now, the second problem, an equilateral prism that's a 60 degree, 60 degree, 60 degree, is made of glass with an index refraction of 1.52. Light enters the prism normal to the surface. What is the total deviation of the light when it leaves the prism? So our instructions are to use Snell's law to calculate the angle of refraction at the first surface, then use geometry to calculate the angle of incidence on the second. I'm going to change those words and upload this again. Surface the light hits, then use Snell's law to determine the angle of refraction at the second surface if it exists. If you have total internal reflection, you'll get no result. You'll get an error from your calculator, and that tells you, oh, total internal reflection. And if it reflects, well, then you keep going. So first, we start with our picture. Now, I am sure that there is actually a geometry tool that would make an angle. That looks about right. So there's a 60-60 triangle. Now, great. Meant to do that. Now we're told that the light is coming in at a normal incidence. So if it's coming in at a normal incidence, let me just set my ruler here. And one more tick, not if I could get it. Okay, that's about normal. So I'm going to have my light coming in like this. So there's my incident ray. Now, we know Snell's law, n1 sine theta 1 equals n2 sine theta 2. n2 equals 1.52, n1 equals 1.00, because air, roughly same as vacuum, we just go with 0. So in this case, the angle of incidence is theta 1 is 0 degrees. Why not 90 degrees? Because we may measure the angle of incidence from the surface normal. This is normal. And so theta 1 is 90 degrees. If theta 1 is 90 degrees, it doesn't take a lot of work to find that theta 2 is 90 degrees. So the light is just going to go straight through here. Now at this second surface, I have to figure out what my angle of incidence is. Now remember, the angle of incidence is the angle from the surface normal. So here's my surface. Okay, I'm going to make this so it's narrow. Here's my surface normal. So now I use my geometry. What do I know? Well, I know this was 90 degrees. I know this is 60 degrees. So if this is 90, that's 60, then this must be 30 degrees. And if that's 30 degrees, then this must be 60 degrees. And then you have to ask yourself, which one of these is the surface or is the incident angle? And the incident angle is the angle between the surface normal, that dashed line, and the incident ray. And so I'm going to have theta, oh, that should have been theta 1 prime. Theta 2 is equal to 60 degrees. So if theta 2 is equal to 60 degrees, let's go ahead and do Snell's law here. Now, in this case, we're going from 1.52, that's index refraction in the prism, sine of 60 degrees is equal to 1.00, that's the index refraction outside, times sine of theta 2 prime. Well, just a little quick math, sine of 60 degrees is 3 over 2, or 0.866. 1.52 times 0.866. Well, I don't know what that is, but you know what it is? It's definitely bigger than 1. If that's bigger than 1, then theta 2 prime doesn't exist. Because sine of theta cannot go bigger than 1. It's got to be between -1 and +1. So that has a definite meaning. That means total internal reflection. So if I have total internal reflection, then that means the light is going to reflect with that same angle. Come on. Like this. And so I have 60 degrees there as well, because the law of reflections, theta 2 double prime, I'll call it, is equal to theta 2. There's our law of reflections where we're measuring the angle from the surface normal. Well, almost done. I say almost done. Could be total internal reflection, but look at that. That is not a very big angle of incidence. In fact, given that we know that angle of reflection is 60 degrees, that means this angle is 30 degrees. This angle is 60 degrees. So the sum of the interior angles for a right triangle is 180 degrees, which makes this 90 degrees. So we end up with theta 3 is equal to 0 degrees, because it's 9 degrees from the surface, which means it's 0 degrees from the surface normal. And so just like with the first one, it's going to come straight out. So I kept my ruler here at the same angle so I can just continue it on. And there it came out. So it did one internal reflection. Now, the question asked us to find the total deviation. So how much did it deviate from going straight? It deviated that much. Notice it's 180 degrees going from the starting to keep going straight. And we took away 60 and 60. So the deviation is equal to 180 degrees, what it would be if it was straight, minus the angle of incidence, minus the angle of reflection. And that's equal to 60 degrees. 180 degrees minus 60 is 60. So that's my total deviation. All right, those are the problems here from chapter 26. If you can do these, you probably should be in pretty good stead for the problems on the test. You will definitely have a ray tracing problem. You will have something like one of these 6 drawings that I did. So if you can do those 6, you know you'll have one of them down. And then you'll have another problem from chapter 26 that will deal with Snell's law. All right, have a good evening.